For this video, we're looking at the second derivative test numerically. So what if you only had values of certain functions? So let's say you knew at x equals 1, f of x equaled negative 2, f prime of x equals 0, and the second derivative was 5. What does that tell you? Well, I know that there's a point. When x equals 1, f of x is negative 2, so I have a point, 1, negative 2. It's on my graph. I also know that because the first derivative is 0, that this is a critical number. My graph flattened out. So at this point right here, the slope is 0. The second derivative is positive. So my graph is concave up. It flattens out, but it's concave up at that point, which means that 1, negative 2 is a relative min. And my justification would be that f prime of 1 equals 0 and f double prime of 1 is greater than 0. If I look at this value, well, I have a point, 4, 7. It's on my graph. And if I look at the first derivative, it's 3, which is greater than 0. So it's increasing at that point. And it also happens to be concave up at that point. But basically, that's all it says. Because this isn't 0, 4, 7 is not where the graph flattens out, so I don't have a max or a min. So basically, 4, 7 is just a point on the graph. If you look at this problem here, or this line right here, the point 6, 1 is on my graph. It's on the graph, and the graph flattens out there. I look at my second derivative is negative, so my function's concave down at that point, so I have a max. And I know that because f prime of 6 equals 0 and f double prime of 6 is less than 0, telling me it's concave down. And that's a look at what you could do with the second derivative test numerically.